Hi everyone, welcome to supplementary video 17. So in this problem, we will be discussing the Graetz problem, and essentially I want to uh, make show the derivation of the similarity transform, which we kind of skipped over in the class because of lack of time. So just to refresh your memory, the Graetz problem is the problem of heated pipe. So we have a pipe which is heated at temperature T wall mentioned as here, and we have a fluid flow which is coming at temperature T naught. We assume that the system is steady, and we assume that the system where the flow is fully developed. So we are saying that the flow is fully developed because the boundary layer thickness of the fluid flow is much larger than the boundary layer thickness of the temperature. So basically we're saying instantaneously, almost as soon as the flow enters, the boundary layer will be thick for fluid flow, and as soon as the boundary layers meet, the flow is fully developed. So that's an assumption. So when we assume that, we were able to basically get these equations which are written here. We also assume that we are solving the problem currently in the developing region, which means that delta T, which is the boundary layer thickness for the thermal portion, or delta T by R, is much, much smaller than 1. So if we allow that, basically what we get essentially is that the convection in the Z direction, so U del T by del Z is convection in the Z direction term, left hand side, is being balanced by the conduction in the R direction. So that's essentially the physical feature is that there is no convection in the R direction because there is no velocity in the R direction, and there is no conduction in the R direction because the delta R is much, much larger than delta Z. There is no conduction in the Z direction because delta Z is much, much larger than delta R. So essentially all the conduction happens in the radial region, and all the convection happens in the Z direction. So that's essentially that physical meaning. Then we have this boundary condition that T wall temperature is simply T wall at R equal to capital R. Note that we need one boundary condition in Z and two in R. Okay. So temperature at the wall is TW and temperature at center is T naught. So if you look at the center, because the double layer is the boundary layer is developing for the thermal region, at the center the temperature will be T naught because it's outside the boundary layer, and so there will be no gradients outside. And at the entry, the temperature is simply also equal to T naught. Okay, so this is the problem setup. We discussed this in class. Then we said, okay, this is okay, fine. How do we proceed further? We said we want to exploit this delta T by R much smaller than 1. To do that, we define this non-dimensional distance from the wall y tilde, which is 1 minus R by capital R. And when we substitute this back in the velocity profile, we get the velocity profile actually simply becomes 2y tilde. This portion essentially becomes 2y tilde. And these curvilinear coordinates, this R and small r here, becomes essentially capital R, which allows us to simplify the equation and obtain this non-dimensional equation by using theta as T minus T naught by T wall minus T naught, and Z tilde as Z by R. So I'm not deriving this because we discussed this in class, and we get this equation where essentially the left hand side has a Peclet number because Peclet number is 2UR by alpha, and we get this equation on the right hand side, which is again basically saying that the convection in the Z direction is being balanced by the conduction in the R direction. But here now we have removed the variables R to make it a Y tilde, that is distance from the wall. Okay. And then we have converted the boundary condition, again, one boundary condition in Z and two boundary conditions in Y to solve the problem. So this is the problem setup. Now we want to solve this problem further, and we typically see a semi-infinite system is when we apply similarity, but we don't really see a semi-infinite system here. But that is actually implicitly hidden in this portion, that Peclet number is much, much larger than 1. So essentially this number here that you see is actually much, much larger than 1. So to do that, let's try to find a similarity variable, and then we can see how this problem is apparently semi-infinite, and will become a little bit clearer. Okay, so when we get this scale, whenever you want to find a similarity variable eta, we want to write this as y by delta t, right? That's typically how you want to write it, y tilde by delta t. And we can, let's also write it as delta t tilde. So to find delta t tilde, what we will say is we'll substitute delta theta is basically simply 1, because you can see the theta variable only varies from 0 to 1, because the temperature can maximum be T wall and minimum be T naught, so it will be between 0 and 1. And note that whenever you have constant boundary conditions, typically this always scales as 1. Unlike when you have flux conditions, then you may have to adjust your delta theta to also depend on y or z. But in this case, that's not the case. Okay. So delta theta is simply 1, and delta y tilde is simply delta t tilde. That's because that's the portion you essentially want to see, that is the dimensionlessly, that's delta t tilde, and z is simply delta z is simply z. So we can substitute this and we get 2 times Peckley times delta t, sorry, delta t tilde into 1 by z tilde gives us 1 by delta t tilde square, or delta t tilde essentially roughly scales as, and we can ignore this factor 2 because that's not important, scales as z tilde by Peckley to the power 1 by 3. Okay, I hope this makes sense. Okay, so z tilde by Peckley to the power 1 by 3. So essentially what we're saying is our eta should be y tilde by z by Peckley to the power of 1 by 3. And we want to express theta as a function of eta. So that's our objective now. So this is essentially how we derive the scaling analysis. But now when we do that, one of the problems is this is not semi-infinite. So how do we solve, why do we use similarity variable now? So let's try to change our boundary conditions. So when y is 0, essentially our eta is 0. So we say theta at eta equal to 0 is simply 1. Okay. Now we say when y is, the value is 1, right? When y is 1, then our eta is actually 1 by z tilde by Peckley to the power 1 by 3, right? And this value is 0. Then finally we have when z is 0, that means our eta is infinity. It is infinity. We get the value to be 0. The important portion here is that this value eta becomes Peckley to the power 1 by 3 by z tilde to the power 1 by 3. But because Peckley is much larger than 1, we can say this value is approaching infinity. And basically we can simplify this and say theta of eta equal to 0 is 1 and theta of eta equal to infinity is 0. So essentially it's kind of saying because of the large Peckley number basically property, we are able to kind of say this is approaching infinity, and that's allowing us to reconcile these two boundary conditions. Okay, so our goal objective next is to convert this equation into eta Okay, so let's convert this equation into eta and see what happens. Okay, so let's do that. So we have del theta by del z. So let's do this together. Del theta by del z tilde is d theta by d eta into del eta by del z tilde, right? And if you look in this here, I have z tilde in with power of -1 by 3, right, in the negative value. And I'll simply basically I'll write this as d theta by d eta, okay, into -1 by 3, because that's the power of the z value, right? And then I'll want to have, I can write this as eta by z, because I'll increase the power of z by 1. So you can actually expand it and try to differentiate by z, but you can verify that this is what you will get. Or I'll write this as d theta by d eta minus eta by 3z. Okay, you can verify this. Then we have del square theta by del y square. So del theta by del y first. Del theta by del y becomes d theta by d eta times del eta by del y, okay, and this becomes d theta by d eta times simply 1 by z by Peclet to the power of 1 by 3, and del square theta by del y square would be uh, uh, sorry, del by del. So let's make it a bit clear. Del, it's not d, it's del square theta by del y square is del by del y of del theta by del y, or this is del by del y tilde of d theta by d eta 1 by z by Peclet to the power of 1 by 3, or this becomes d square theta by d eta square times del theta by del eta by del y 1 by z to the power roughly 1 by 3, or essentially this becomes d square theta by d eta square one by z by Peclet to the power of 2 by 3. Okay, so it's a slightly long derivation, but I hope you can follow this. So do this yourself. I've kind of maybe done a little bit faster, but let's now try to substitute this back and see what happens in the problem. So our equation is 2 Peclet. So equation is 2 Peclet times y tilde. So we have a y tilde here. Then we have del theta by del z. Del theta by del z is here. Okay. So 2 Peclet y tilde, and then we have d theta del theta by del z, and which is this value. So let's write it there. Minus d theta by d eta times eta by 3z tilde. There should be a tilde here. Just to correct this tilde. Yeah. Okay. And the right hand side is del square theta by del y square, which is simply d square theta by d eta square times 1 by z by Peclet to the power of 2 by 3. Okay, so we get this here, and then finally, if you closely look this up, this becomes y minus 2 by 3 here. Okay, d theta by d eta is a pretty clever problem here that you can see this as this becomes z tilde by Peclet. Okay, is d square theta by d eta square by z by Peclet to the power of 2 by 3. Okay, and this basically gets cancelled and this becomes 1 by 3. Okay, so you could cancel this out and this becomes 1 by 3, and furthermore this portion essentially is also eta, because we can't have z and Peclet y coming around in final equation, and this does become eta, or this becomes minus 2 by 3 d theta by d eta square is equal to del square theta by del eta square, or final equation is del square theta by del eta square plus 2 by 3 eta square d theta by d eta is equal to 0. And let me check if this equation is incorrect or not. That is correct. So this is what you get as your final equation. And again, boundary conditions reminding you is 1 and theta at eta equal to infinity is 0. So you can solve this problem, which leads to essentially a gamma function, but we are not going to be discussing that. Okay, so let's quickly review what we discussed in this video. So we first said this is the problem where we wrote the boundary conditions and the governing equation. We changed the variable from y tilde because we wanted to exploit this property of delta t by r much more than 1. And then we non-dimensionalized to get a Peclet number in our final equation here. We said it doesn't really look like a similarity problem, but because of this high Peclet number, it does become a similarity problem. And what you essentially do is you kind of rescale everything by delta t. So by using the governing equation, we find the scale of delta t to be this. When we substitute, we can reconcile the boundary conditions because of a large Peclet number, where eta value becomes very large. So we can say that's all actually infinity. and then we basically took partial, derivatives with respect to z, y, and so on. And then finally, we were able to get ODE at the end. From here, we went on to calculate Nusselt numbers. We did that in class. And I think this problem will be very useful for you to kind of practice this supplementary video, because then you can also solve your homework 5 problem 3 very easily, where there's a Sherwood number which you have to calculate based on similarity method, where you get error function as the solution. Okay, so I hope this video was useful. Feel free to let me know if you have any questions, and I look forward to seeing you in the next video.